Hey guys, welcome back. Moving on to question 9, part B of the CXC CSEC Math January 2012, part 2. We have that the diagram below shows the graphs of three lines and a shaded region defined by the three inequalities associated with these lines. So this is the graph. These are the three lines: x equals 6, x plus y equal 40, and 3y equal x. The inequality associated with the line 3y equal x is 3y greater than or equal to x. So let me just show you what that looks like. So 3y greater than or equal to x, that's here, so that's everything above the line, 3y equal to x. And then part 1, we want to state the other two inequalities which define the shaded region. Well, for x equals 6, we want everything to the right of that line. So we would look at x greater than or equal to 6. So for x equals 6, the inequality we want to look at is x greater than or equal to 6. And that would give us this region here. Right, everything beyond to the right of x equals 6. And for x plus y equal 40, we want the inequality x plus y less than or equal to 40. Right, because we want everything below this line. And so that would give us everything. I'm going to draw the line in this direction. That would give us everything here. Right, and where these three lines intersect is in this region here, which we call the feasibility region. So let me clear this off and show you. So when we use those inequalities, 3y greater than or equal to x, that's everything above. X greater than or equal to 6, that's everything to the right of x equals 6. And x plus y less than or equal to 40, that's everything less than or equal to, that's everything below here. We get this region here, which is already shaded. And this is our feasibility region. Right, that's that region there. Now we're given the function p equals 4x plus 3y, and we're told that it satisfies the solution set represented by the closed triangular region, represented by the feasibility region. And the function p equals 4x plus 3y is called our optimization function. So in part 2 and 3, we want to do the following. We want to identify the three pairs of xy values for which p has a maximum or a minimum value, and we want to find out which pair of xy values makes p a maximum, and of course justify the answer. So you'll answer two of them simultaneously. So firstly, I would say that for systems of this kind, so where we're given a system of linear inequalities and we have an optimization function, somebody really smart proved a long while back that the maximum or minimum value of the optimization function lies on the vertices of the feasibility region. So this is our feasibility region. The vertices of the feasibility region is, in this case, is this point, and this point. And so the maximum or minimum value would lie on one of these points. And so that's the three pairs of values that they want us to identify. And then which pair? Well, to find out which pair, we actually plug the points into the optimization function, and whichever value gives us the maximum value, that's the point that we use. So let me just state what these points are. So this is what I think each unit, each tick on the x-axis represents one unit. So that's 1, 2, 3, 4, 5, 6. So that's 6 what? Let me go back here. Let me clear. Let me clear that. Right, so the points are 6, 6, 2, 6, 3, 4, 6, 34, and 30, 10. So let's just draw up a table. Call this x, y, and p equal 3 equal 4x plus 3y. x62, 634, and 30, 10. When x is 6 and y is 2, we get 30 here. When x is 6 and y is 34, we get 126. And when x is 30 and y is 10, we get 150. So since this point, since this point here, 30, 10 gives our optimization function the maximum value, and it's a vertex on the feasibility region. This here is the point that makes the optimization function have its maximum value. If we were asked for the minimum, then this would be the point we look at. But we're asked for the maximum, so the maximum point is 30, 10. And that's it.